Hello dear students, hope you all are doing well. Today through this video I am going to start a new chapter. The name of the chapter is Chemical Kinetics. So in this chapter the first topic which we are going to study is rate of chemical reaction. So rate of chemical reaction is defined as change in concentration of a reactant or product per unit time. So to understand this better, let us take an example. Say you have a reactant A which undergoes chemical reaction to form product B. Say at time T1, the concentration of reactant is A1 and concentration of product is B1. At time say T2, concentration of reactant is A2, concentration of product is B2. So we can express the rate of chemical reaction either in terms of reactant or in terms of product. So first let us see how we can represent the rate of reaction in terms of reactant. So rate of reaction in terms of reactant. So rate is equal to, now since it's defined as change in concentration of reactant, so when you're writing the rate of reaction in terms of reactant, in numerator you write the change in concentration of reactant. So we'll write here change in concentration of reactant by change in time. Now we know change in concentration of reactant is equal to final concentration of reactant minus initial concentration of reactant. Similarly, in denominator, final time minus initial time. So from this chemical reaction you can see the rate of reaction is taking place from A1 to A2 for reactant, from B1 to B2 for product. So for reactant the initial concentration is A1 and the final concentration is A2. Whereas for product the initial concentration is B1 and the final concentration is B2. So rate of the reaction in terms of reactant is represented as A2 minus A1 by T2 minus T1, which implies delta A, that is change in concentration of reactant, by delta T. Now, in case of reactant, the concentration always decreases with time. That means the final concentration of reactant is always less than the initial concentration of reactant. But the rate of reaction cannot be negative. So what we do, we multiply here by a negative sign, so that the negative value of change in concentration of reactant multiplied by this negative value becomes positive, and the rate of reaction will be positive. Similarly, the rate of reaction in terms of product is equal to change in concentration of product by change in time. So which will be equal to final concentration of product minus initial concentration of product by final time minus initial time. So if we check the product, the final concentration is B2, initial concentration is B1. So it will be B2 minus B1 by T2 minus T1, which is equal to delta B by delta T. Now when you are writing the rate of reaction in terms of product, you don't need to multiply here by negative sign, because in case of product, the final concentration is always greater than the initial concentration. So the difference is always positive. Let us take a reaction and try to write the rate of reaction. So let us take the formation of ammonia, that is nitrogen plus hydrogen gives ammonia. So if you balance this equation, multiply here by 2, here by 3. It is in gaseous phase. So rate of reaction is equal to, if you write in terms of nitrogen, change in concentration of nitrogen by change in time. Now if you look at this reaction, the stoichiometric coefficient of nitrogen is 1, hydrogen is 3, and ammonia is 2. That means the rate of hydrogen in the reaction is 3 times more than nitrogen, whereas the formation of ammonia is 2 times more than nitrogen. So when we write the rate of reaction for such reactions where you have stoichiometric coefficient, we have to reduce the rate in order to write equal sign. Is equal to. Now since this is a reactant, we put here negative sign. For hydrogen, delta H2, that is change in concentration of hydrogen by change in time. Now the rate of hydrogen is 3 times, so we'll write here 1 by 3. And since it's reactant, we'll put negative sign. For ammonia, is change in concentration of ammonia by change in time. Since it's twice, it's 1 by 2 here. So this is how we can write the rate of reaction in terms of reactant and product for a chemical reaction. Unit of rate of chemical reaction. So we know rate of chemical reaction is change in concentration of reactant or product by change in time. So the unit of concentration is mole per liter, time is second or minute. So the unit of rate of chemical reaction is mole per liter per second. The next topic which we are going to start in this chapter is rate law. Now, according to Rate law, the rate of a chemical reaction is directly proportional to the product of the molar concentration of the reactant raised to the power their stoichiometric coefficient. So let us try to understand this law with the help of an example. So A plus BB gives product B. So the reactants here are A and B, that is capital letter A and capital letter B. Small letter A is the stoichiometric coefficient of reactant A. Small letter B is the stoichiometric coefficient of reactant B. So according to Rate law, the rate of the reaction is directly proportional to the product. Product means multiplication. Product of the molar concentration of reactant. So that is concentration of A multiplied by concentration of B, raised to some power which may or may not be equal to the stoichiometric coefficient. So let the power of A be x and B be y. Now here in this Rate law, x may be or may not be equal to A, y may be or may not be equal to B. It depends on the nature of reaction. So next, rate is equal to. Now if you replace the proportional sign with an equal sign, you need to put a constant. The constant we use here is k. A to the power x, B to the power y. Now k represents rate constant of a reaction. Let us take an example. H2 plus I2 gives 2HI. So rate law, rate is equal to rate constant, concentration of H2 multiplied by concentration of I2. The stoichiometric coefficient here is 1, here also is 1. So this is how we write the rate law equation. Next, let us try to define rate constant of a reaction. So according to Rate law, rate of a reaction is equal to rate constant multiplied by the concentration of reactant. If you have one reactant, you just write the concentration of that reactant. If you have more than one, they will be multiplied to each other. So let us take this reaction. AA gives product B. So you have only one reactant here, that is capital letter A to the power x. Now, if concentration of reactant is 1, that is unity, then the rate of the reaction is equal to rate constant. So rate constant is defined as the rate of reaction when the concentration of the reactant is unity. This is how we define rate constant. The next topic which we are going to study under this chapter is order and molecularity. Order is defined as the sum of the powers. Sum, that means addition. Sum of the powers which is raised in rate law equation. So you have this reaction AA plus BB gives product B. So if you write the rate law for this reaction, rate is equal to rate constant A to the power x, B to the power y, where x may or may not be equal to A, y may or may not be equal to B. So the order of this reaction is equal to x plus 1. Let us take an example. So you have H2 plus I2 gives 2HI. So if you apply the Red law for this reaction, this red constant, concentration of H2 to the power 1, concentration of I2 to the power 1. So the order of this reaction is equal to sum of the powers, that is 1 plus 1 is equal to 2. Next is molecularity. Molecularity is simply the number of molecules of reactant involved in the reaction. Say for example, this reaction, you have 2 molecules. So therefore, the molecularity of this reaction is 2, or we can say bimolecular. If there are 3 reactants in a reaction, is known as trimolecular, or molecularity is equal to 3. Let us take one more example to understand order and molecularity. So PCl5 decomposes, PCl5 phosphorus pentachloride decomposes to give phosphorus trichloride and chlorine gas. So if you apply the Red law, red is equal to red constant, concentration of PCl5 to the power 1. The order of this reaction is 1. Molecularity, since there are only 1 molecule in this reaction for reactant, molecularity is also 1, or is also known as unimolecular reaction. So thank you. In the next video, we'll study integrated Red law equation.